I was like, I need to look back on this.
Yeah, we are starting right now. But part of the reason I showed you some of that is because I want to show you something that's extremely cool. So what I would like you to be convinced of, I'm going to go back and erase some of this just to make sure it stays kind of clean. This is a formula. So W is the weight, but notice the unit is not pounds. It's exactly like that 360 was over there. It's pounds per foot. It's just X, I put X in, and now I can figure out what it is anywhere I happen to choose to break this. Does that make sense?
Are those are foot times pound?
Divided, it's pounds per foot. So earlier, and you're more comfortable with this because of numbers, but earlier when I said, hey, that's 24 feet, we said 360 pounds per foot times 24 feet. Well, notice the feet cancel and you end up with pounds. So that 4320 is pounds, and that's why 360 is pounds per foot. That literally means there's 360 pounds every foot. Well, because it's a triangle, unfortunately it's not. It goes from 360 to 320 to 280. I mean, it marches down the line and gets shorter and shorter and shorter. And keep in mind, because of that triangle, even if you moved 1 inch to the left, it's not 360 anymore. Right. It's like down to 359 and then 357 and so forth. So in a sense, it might even be nice to change that to pounds per inch. But it's a continuous load. It's changed one inch later. It's not even 360 anymore. So do you agree that that 15 times x minus 10 is kind of cool? Because notice, if you throw, well, x is 34 in, which is all the way to the right. 34 minus 10 is 14. 14 times 15, I hope is 360. Like it's giving us the right answer to the right side of that. Our formula is working.
I was just trying to think of 15x minus 10, that slope is the feet, like you said, and the extra x minus 10 is kind of the distance.
That's exactly right. Just like we had to take 360 times 24 to get a weight, you have to take that 15x minus 10 times this distance right here, which is also x minus 10, and then times a half to get the weight of that entire red rectangle. Just that's exactly what we did with 4320.
We're multiplying those together.
It's pounds per foot times feet. So the feet cancel, which gives you pounds. In other words, 360 pounds per foot times 24 feet. Oh, feet are on top, feet are on the bottom. Oh, that's pounds. So basically what that's saying, and what it said yesterday, is every foot there's a new 312 pounds. But because it's continuous, it's not just here's one and then you move a foot and here's another one. It's more like every inch there's 10 pounds. You know what I'm saying? And it's like solid pounds all the way across this. It's calculus. There's a billion of them. So that expression W is a weight of pounds per foot. That's a linear distributed load. And so there's a billion of those arrows. You can only just draw in a few of them to kind of make sense of it. Does that help a little bit? Now, so if that's the case, do you agree with that complicated formula right there for what's going on? Now, if you don't below that, let's see if I wrote this down somewhere.
So we have the negative sign accounted for being in front of 15.
No, that's positive because we took the 2592, which was positive, and the 1080, which was negative, and we added them and we got a positive. We got a positive 1512. So that 1512 is actually positive. It's going up.
Our slope, we had a negative. Why was that? But then are we just kind of ignoring that? Or
No, we need it. We need it. I left that out on accident. We need it. Good job. And I didn't leave it out down below because you have a negative down there.
That is, okay.
Let's see. So if I solve this for V by adding V to the other side, then I get V equals negative 15 halves x squared plus 150x plus 762. I think. Yeah. But do you remember the pattern yesterday? How we took shear and we said, geez, oh Pete, what are you doing? We took shear and we said, hey, if you want to move down to moment, all you have to do is take the integral. Well, it turns out that pattern continues. In other words, if you wanted to move from that distributed load up there down to shear, you could have just taken the integral. Wait a second. So what you're saying is that negative 15 times x minus 10, which is actually negative 15x plus 150, all right? You're saying if I took the integral of that, I could have got that shear down there that we just got? Is that what you're saying? Yep, that's what I'm saying. The integral of 15x is the squared, and then you divide by 2, so you get negative 15 divided by 2x squared. The 150 grows in x, and then you have some constant added on to the end of that. I was calling it b for y-intercept the other day.
So how do you get the 762?
Yeah, so let's back up a little bit because we did jump ahead. Didn't we sort of forget the 0 to 10 thing? So what happens in that portion where x is from 0 to 10? If I make my chop right there, I got 1512 on the left pushing up, and I've got this shear force right here pushing down. I haven't made it to the triangle yet, so that's it. There's nothing else. Do you agree? So that means 1512 minus v has to be 0. Oh, the shear in that entire section, because there's no other forces, is just 1512 the whole time. All the way from 0 to 10. Any place you go, 1512 is the shear everywhere. Are you okay with that? Well, would you agree then that v of 10 is still 1512? Or maybe I should say 9.999. But even at 10, remember the triangle hasn't started either. Now, when there was a 312 there, if you went to 10, then it'd be like an argument. Did 312 get there or not? But remember, 312 is per foot. And even if you just got to 10, is there an entire foot at 10? No, there's a billionth of an inch there. So your 312 is tiny, even still. So that's the key to how I find this unknown. In other words, you say, okay, great. Well, this is your shear right here for that section. Well, you know that when x equals 10, the shear has to be 1512 because that's what it was right where the triangle started, right? So throw 10 into that expression for x and throw 1512 into this expression and see if you don't get 762. It's got to be that leftover. Don't want to leave it off constant of integration.
And throw 10, you have to throw it in B as well.
So,
Oh, 1512 there.
so in kind of the pink example, I mean, I'd really be throwing it in up here, like x is 10. B is 1512, and I'd be solving for B.
I got negative.
Is it negative? Maybe I wrote it down wrong. I got positive.
Because it's negative 15 over 2 x squared
So the x squared is positive, so you have 100 times 7.5, so that'd be negative 750. And then you're gonna add that to 1512, so you'd have 1512 plus 750. And then you'd be subtracting 1500 from that. No, it's positive.
So I got negative 750 and positive 750. That's squared.
So the 10 squared is 100. And then times negative 7.5, that should be negative 750. And then to solve for, to work your way, since this term right here would be negative 750, then I'd be adding it to that 1512. And then here, 15 times 10 is 1500, that's a positive, so I'd be subtracting it. So you end up with 1512 plus 750 minus 1 minus 1500. D is left to be 762. Do you agree with that?
I can't make my calculator do negative 750 and then that way it adds up, but I like on paper, I know it should be that way. I've like thrown the negative sign in and out of the parentheses. I put the squared in and out.
Let's fix it.
Yeah.
Because it's not being squared. You understand the squared is x.
Yes, so originally I did it like that, and then I switched it to these two. I did the negative sign in there, the negative sign out, like I can't get it to spit out, but I won't.
So this is, yeah, these are both correct. So you basically collected everything on the 7, you got a positive 750. That's what's left on the right hand side. So now you have 1512 on the left.
Yep, and so you'd have to subtract.
You have to subtract that one by
Oh.
750 because it's positive on the right hand side.
Okay, I understand.
I have one. I should have been walking this whole thing.
I'm going a little too fast too.
So,
Almost 7,500. Well, so is the negative 150 over 2 times 100 is 15 over 2. Yeah, okay, well that price on.
there we go.
Thank you.
There's a 0.
Who says zeros don't count? They do. They do count. Okay. So we're still processing, but it's like, okay, then what happens when you work your way? Because again, there's 3 sections here and they all have to be different. We have totally different equations that are modeling this. What happens from 34 to 40?
You have the positive 1512. Oh, you should have just had the 4320, right?
That's exactly right.
And then I guess we're making it 40, so do we have that positive?
Well, we're saying it's everywhere between there. We're not actually making it. We're saying it's everywhere between there from 34 to 40. So we could be at the left-hand side. We could be here, or we could be anywhere in between.
We actually get that.
Yeah, I mean, eventually, yeah, we do. When you're very much at the end. And so the point is that 2808 isn't part of this because remember, X can be anything. And I said technically less than 40. So it's like, it isn't quite getting there, if you will. So that's it. The only thing we really have then is the shear of the beam anywhere in there to solve that. So if I say, oh, okay, that's 1512 minus 4320 minus V. That has to be 0. Then I get V equals negative 2808. Now, why is that particularly cool that we got that answer?
That your is actually. Oh,
We
man.
calculated that somewhere else.
And it equals that end number so that it gets back to 0 again. So like once you actually make it all the way to 40, back to 0. Against my better judgment, We'll see if I'm right or wrong about this. Let's go try to just do this in Desmos right now. The only reason to say better judgment is because I'm doing this in the app, so I can copy it over. I'm a little worried it's going to be wonky. So we said y equals 1512. And then we said the second one was y equals negative 15 halves, but I'm just going to call that 7.5 x squared. And then we said it was plus 150x.
Why?
And then plus 762, right? Tell me if I typed something wrong.
Yeah, you have one minus. Instead of one.
I left the equals off. So it is negative. So there we're okay now. Thank you. And then y equals negative 2808. Now, cool nerd trick. So if I go up here and I say bracket, hope I can do this in this version. If I open a bracket and I would say this exists from 0 to 10. To 10, and then I close that thing off, then that line is only going to exist from 0 to 10. So let's go see it. So notice it's at 1512, so it's like, oh, there it is. And then it switches to that blue equation, and so this exists from 10 to 24. 10 less than x less than 24, close that bracket off. Bam, then it takes off from there and goes down. And then this last one exists, and this is what I can't do very well, is like copy and paste thing. I can copy and paste a lot better. And this goes from 34 to 40, correct? 34 less than x less than 40, bam. All right, there it is. Now, of course, this looks terrible, right? Like I can't really see it very well. Let's just think about it. You agree the top of it is at 1512, right? And then down here, I don't see anything. Oh, that's because it's way down there. There's 34 to 40 right there. And then like, where's the blue graph? And so forth. But watch this. So I'm going to go to the wrench up there and I'm going to say, now that I see what's going on here, would you agree my x's really should be from 0 to 40? And my y's we just saw went from negative 28 up to 1512. Notice the bottom's already at 2904, close enough. So then I'm going to switch this one to 1512.
So I think you might have missed.
Yeah, so
Yeah.
this is 34. That's why it wasn't connecting. So, aha, there we go. There's my shear. Now, there is actually kind of one thing that's technically missing here, because what happened when it made it to 40? It went to 0. So actually, the part that's missing in this is if I went over here and said x equals 40 vertically, but then I said, oh, yeah, that's cool, except for I would like the y values to stay between 0 and negative 2808. So negative 2808 less than y less than 0. So I would have just drawn that with a pencil, but it's like, that's the diagram now. Now notice it's not labeled. I really need to see the 2808 and the 1512 there. So that's not good. But notice it's kind of cool because it's sort of smoothly connected. The other reason that this is cool and why I decided to try to do this in here is because I can, oops, take a picture of it after. I'm going to blow it up so it's more batter. And I can drag it back into our drawing over here to keep it for later.
This is what I would be doing.
This is what it's.
I'm trying to Digging the old school.
Yeah.
Good digging.
So just to quickly throw these in here, we're saying, hey, that's at negative 2808. And this was at 1512, and I could add these labels in Desmos, but this is really shear in feet. Nope, not feet. What is it? Pounds. Shear is a weight. And this is X in feet. What else would be nice to have on this drawing?
X.
X intercept. That's exactly right. So calc that for us. How do you calc that?
Take the derivative of
Nope.
We
Easier.
set it equal to
You set that equation equal to 0. Unfortunately, what kind of equation is that equation? It's quadratic. So since that dude is y equals negative 7.5 x squared plus 150 x minus plus 762. I need to know when y is equal to 0. Y equals 0. If I throw that in the quadratic formula, I get 24.2. Now back in Desmos, could I have stole that for free? Yep. Isn't that cool? Y equals 0, x equals. Yeah, it kind of depends on how you have the equation typed in there. So
How to zoom in to like, you know, the plane scale to see.
So that's kind of cool. It would be kind of nice to just, you know, have copied that picture over, right? But it's just kind of neat to see that you can do it algebraically. So it's really 24.2. I think I said out loud it was 0.3, but I wasn't looking at my notes very good. And notice that kind of agrees with the picture, right? I can see it's a little past 24. So even just visually. So of course, the takeaway from this is the max, which is, notice I'm writing down positive because I don't really care, as we said yesterday, is it being going down or up? You know, it's like whatever, it's shearing, who cares? Where did that happen? Where's that going to happen? Like, okay, we put the weight on it and we chose a beam that can't handle 2808, and then we loaded it all up like this, and then where's it going to break?
It kind of makes sense with our diagram.
So it makes sense it's going to break in that 34 to 40 range. Now, where is it being pushed on though?
And
It's being pushed on right over there at D. Like that's where it's going to break. It's going to break right there. Oops, that's not the right choice. It's going to break right there, right on the corner. Now notice where, and this is why in engineering classes, they put a triangle there, because notice that has width, like that's 5 inches wide right there. So it's actually going to break where I showed, but notice now the 6 feet isn't 6 feet. So they draw a point just to like make it so that you don't have to think about this stuff, but you actually do have to think about that stuff. That's a thing. As far as your calculations go, you kind of ignore it, but that's where it would actually break.
So in like the real world, if that block that's sitting on there is like 6 inches, you would say that it would break at 39 pieces.
Yeah, that's exactly right. So although the shear all the way through the beam is right there, that's actually, does it make sense? Everything to the right of that is not going to go down, but the rest of it does want to go down. And so that's the transition. So that's where it's going to break right there.
But because our triangular load is not over the beam right there, it doesn't really matter. Our calculations, we just track that. So like if that triangle load is going over the.
Yeah, that's right. That would make it a little more complicated because we'd technically have to take, or we could technically take that off because it's supported all the way across there. You see what I'm saying? So we could say, oh, this beam isn't really 40 feet long. It's 39 feet 6, you know, and that's a part of BC Calc. Like if I say in there, I want a beam that's 40 feet long, it'll ask, is that 40 feet from clear span? In other words, there's nothing supporting that 40 feet, or is that end to end? And I'll say end to end, and then it'll say, well, what's your supports? And I'll say 5.5 inches, and it'll actually calc that in there. So it doesn't, it treats the clear span as 5.5 and 11 inches shorter than 40 feet. And that way, you know, it's actually accurate, which is kind of rad, isn't it?
All right, I'm ready to get hired. Come on, guys.
Let's do this. Okay, so now unfortunately, I don't think I can move that. But does it make sense? What we saw the other day is, well, let's do the moment with calculus again. Let's take the integral of those equations to get our moment equations. Fortunately, though, I've got them kind of labeled down here. I'll go ahead and write them all in just so we have them, so we can see them. This is y equals 1512.
And we will, unlike last term, only be taking the integral to find the moment. You don't need to do whatever we were doing last time, that complicated.
We got to do what we did on Tuesday, which is the whole thing.
Because ultimately we could just take, oh, no, so create a C, and create a constant. Or- no,
So this one would be 1512x. The moment from 0 to 10 would be 1512x because the integral of 1512 is 1512x.
But we're just finding the integral of each one of our.
That's exactly right. Yeah. So remember, there is kind of a plus b there. Like when you take the integral, there's a plus b, but the moment is 0 at x equals 0. Therefore, the b is 0.
There we go.
Because, and the reason the moment, do you understand why the moment is 0 there?
Because that's the maximum, or the shear is gonna be.
Yeah, the issue is if x is 0, then you have no distance. So you have 1512 times the distance. Isn't that what moment is? Because remember, we're actually finding the moment around this point right here. And so the moment around that point would be x times 1512. But if x is nothing, then you got 1512, but you got no distance. So that's why the moment at that point is nothing. That's not obvious, I don't think, which is why I took the time to talk about it. Okay, cool. So what about the hard one from 10 to 34? What about that? Well, what's the integral of negative 7.5 x squared? Well, I take a cubed and then I divide by 3. 7.5 divided by 3 is 2.5, surprisingly. Cubed. And 150 x squared, but you divide by 2. 150 divided by 2 would be 75. And then you got 762, but that turns into 762x. And then you got your y-intercept. But what did we just learn a second ago? We learned that all the way, let's see, actually, no, we got to make a calculation. Like back in this previous problem, when m is 10, I'm going to do this in red. Back in that previous section right there, when x was 10, does it make sense the moment was 12 times 10, which is 15,120? So does it make sense? That's where 0 to 10 left off, and therefore the moment's got to start at the same location. So that means down where we are, we're saying when x equals 10, the moment has to be 1520. 15, 12, 20.
This is kind of what we did.
Yeah, that's exactly right. Yeah, we did some stuff like this. That's exactly right. It's like, where did it leave off? So if I throw x as 10 in all 3 of those locations, I throw m as 15,120 in there, I can find out b, and b turns out to be 2,500.
Actually, plug in
10 for x. 10 for all 3 of those x's, 15,120 for that m, and add all those other numbers to the other side, and that leaves b being 2,500. Again, feel free to punch that in quick if you want to kind of check that that's the case. Well, armed with the same logic, then where does that leave off? In other words, when I make it to 34, what does that crazy expression, that cubed equation, what does that cubed equation spit out?
It's out. Oh. So I got negative
No,
plus.
should be plus.
I guess.
But yeah, check it.
It's the same issue, or I have to do it in my head. So what was the question you said was that huge?
So then, now that we have this moment equation, remember that lives from 10 to 34. So again, just like we did a second ago, we want to say, well, what does it leave off with then at 34? So if I throw 34 into my equation, with that 2,500 in for B now, I get out 16,848. Which is where the next one will start.
So for the purple 10 is less than X less than 34, we're plugging.
I'm going kind of fast because I already have this calculated, so.
Are you changing the value of them?
So the thing that you got to see is the business of it. You know, what did it start at? Like our first one, 0 to 10, it started at a moment of 0, but then it ended at a moment of 15,120. And then we said, oh, purple equation. Oh, well, then that starts at 1520, but then where does it end? And we just figured out it ended at 16,848. And therefore, 16,848 is where our next one's going to start. So when I take the integral of this one, the integral of negative 2808 is negative 2808. But now it grows in X. Yeah, let's double check that. So that's really negative 2.5 times 1,000. So that'd be negative 2,500.
That's what I did. I got it. I missed the negative on 2.5.
Got it. And so based on where we just left off, then we say, okay, well, when X is 34, we were supposed to get 16,848 left off from the last location. So what does that give me for B? Hence, B equals huge number, 112,320.
Sweet. That's it. First time all day. No, I had to struggle.
Let's go back to Desmowski. And by the way, in terms of saving some trouble, watch what I do this time. Instead of calling these y, like I did before, and I'm actually going to go turn all those off so that they're not in the way. I'm going to say this time f of x. I want you to see if you can figure out why I'm doing this. Same thing, doesn't change anything, it just graphs it. But our first equation we said was 1512x, right? That's not what I've written down for some reason. 1512x, is that right? Now, why did I do that? Well, a second ago, once we knew that equation, we said, oh, what is it at 10? Now, in this case, it's times 10, so it's really easy. But couldn't I say, why don't you just do it for me? Why don't you just tell me what f of 10 is? Oh, okay, it's 15,120. Then we moved on to our second equation. Well, I can't call it f again, so this time I'm going to call it g of x. And we said that was equal to negative 2.5x cubed X. Thank you. X. Where is that? There it is. To the third arrow, that dude to the right, and then we jump to plus 75x squared. And then to 762x. And finally to plus 2,500. And while we're here, since I forgot it a second ago, what that was from 10 to 34, right? So 10 less than x less than 34, close that off.
So we can find the 2,500 by finding the g of x.
Exactly. So we want to see where this ends. Well, rather than having to bust out our calculator, we can say, sweet, since I wrote it that way, then how about you tell me what g of 34 is? Bam, undefined. Why is it undefined? Nice. That's exactly right. Now you can fix that by going in here and saying less than or equal to. I just did an equal sign and now all of a sudden it pops up 16,848. Okay, cool. And this one up here, we actually said it lived from 0 to 10. I'm going to put the equal sign in here so that that other calculation works. Now that I limited it, that f of 10 would have went away. You understand that? And then finally, I don't really need to know the end of this, but I'll go ahead and do it anyway. H of x. That equals negative 2808 x. And then we said plus 112,320. And we only want to see that from 34 to 40. Beautiful. So it's kind of a parabola looking structure. Notice it tops out at 30,000. So in terms of its limits, it's like 0 to 34, and then I want to be 0 to 30,000, and I'll have a much better view, right? So 0 to 40 and 0 to 30K. Ah, beautiful. Now, again, our goal here is to find the maximum of that. If we're in Desmos, we just kind of click there and go, there it is. All right. But what do you notice about the x coordinate of that? Yeah. And of course, from calculus, we say, oh, do you want to find that mathematically? Oh, yeah, that's a unique point on there. That's where the slope is 0. What do you do to find the slope? I take the derivative. Wait a second. We just took the integral of shear to get this. Therefore, we already have the derivative. It's the shear equation for that. And where is that equal to 0? Oh, that was the x-intercept. And so it's actually not a coincidence that that's the case. So all I really like, everything I just did, 40 minutes or whatever, is to get 29,432. Do you agree with that? That's all I really need to know is the maximum moment, because that's going to tell us where it's going to break. And then notice, because of the weird loading, it's not in the middle of the beam. It's not at 20 feet. This is basically saying it's going to break at 20, just a hair past 24. So if you load it as you said, but you put the wrong size beam in it, it's going to go snap at 24. Now, realistically, will it actually be the case? Well, you watch the factory build these things, is exactly the same amount of glue in every place. Well, it was pretty structured the way they did it. It's not going to break far from there, but you get, it's a tree. Some trees grow faster than others. It might not break exactly, like if you put a mark on it, just measured perfectly 24 feet 2 and like made a mark and then loaded it, is it going to snap exactly right there? No, but I bet it'd be within an inch or two based on just material strength and so forth.
Brand new machines.
So, out of curiosity, when I look at our moment from 0 to 10, we have 15x plus b equals 0, blah, 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 blah. If we just took that moment naturally from 0 to 10, we would have,
Like if we did it ourselves?
yeah.
Yeah, that's
Well,
a good
because
question.
I'm thinking we could save a lot of time if we started with the moment and then took the integral or the derivative and then get the shear that way.
Yeah, the problem is because moment is a force times a distance. The shear is the force, and now you just have to add distance to it. So it's like by doing the moment, you will have, in a sense, already done all the other ones anyway. In a sense, it's actually way easier to make that W and then integrate it down because moment is so much harder to calculate. But you're exactly right. Let's go back over there.
So I'm thinking if we took that, we'd have the moment going this way. We'd have 1512 plus n, or however we orient n equals 0. And then n would equal 15. I guess we wouldn't have that x above.
I mean, that is an excellent exercise. I'm gonna go ahead and write this in here really fast. Moment in foot pounds, and then we'll go look at that. And this is x in feet. And that would be your moment max right there.
Because I was just thinking, like, if I really didn't know, that was like such a weird load. So I was looking at our next one, the next one. I was like, what if we didn't have that like bottom one before we give it to
Right.
us? I was like, that's so weird. Like, how would I find that? I mean, if you did the moment first, then I would still have to, but then you wouldn't have to mess with that at all. You could take the shear.
But keep in mind that you know, there's your shear right there. That's the ugly shear, 15x squared. And so moment is a force times the distance. Well, what's that distance? How far is that away? Does it make sense? It's not x away. The location of that is a third of the way in. So you'd have to take this distance right here, which is x minus 10, and you'd have to figure out what a third of the way in there is. Because that's its location. But where is that? Whatever this distance is right here, I've got to take kind of 2/3 of it and add it to 10 over here to get that location. So it's kind of painful, but that's in the end why it turns into being an integral.
Yeah.
Because the third, like we took squared and then we raised it to the third power and divided by 3, see the third in it? Like that's where that third is coming from.
So could we take the 15x minus 10 times x minus 10 and then multiply that again by,
That's exactly right. Times a really weird distance.
and then you get whatever, right?
So I'll erase this just because it'll look confusing, but it'd be like exactly what you just said, but then it'd be like, okay, well, this distance right here is x minus 10. And so I'd have to take a third of that. And so that would kind of be this distance, a third right there. So then it'd be like the entire x minus a third of that x minus 10. And then that would be this distance right here. And that's actually how far away that single load really is. So I'd have to be multiplying it times that. Now I can find a common denominator and so forth, but it's actually taking the integral to get it is actually easier. That's painful.
That throws off on the test.
Again, just because I think it's such a shame not to do this, but notice we got a V max, a shear max of 2808 and a moment max of 29,000. So it's like 2,800 and 29,000. So let's go to this chart, which I loaded since yesterday. So remembering that shear is kind of this column and moment is this column, I'm looking for 2,800 and 29,000. Notice, as we saw yesterday, if you get to 29,000 in moment, you're way beyond what you need to be in shear. Yeah, it's more like you're just looking for 29,000, right? And it was 29,400, so this one wouldn't quite do it, but this one would. So notice you can do a 3.5 by 16-inch beam, or you can do a 2 5/8 by 18-inch beam, or down here, you could do a 5 1/4 by 11 7/8. Any of those three beams would serve the purpose. If one's cheaper, if one's lighter, whatever. Incidentally, just with respect to weight, notice this one is 12 pounds a foot, this one is 14 pounds a foot, this one is 16 pounds a foot. So that bottom one is a lot heavier. And if you think about it, you should understand why that is, because remember how the moment of inertia was width times height cubed. So the height is really important. So if you move to that bottom one that's 11 7/8, and you say, oh, let's just use a short beam. Well, you just took away the strongest contributor to its strength. And by the way, that's what we'll be talking about on Tuesday is the last part of that calculation. So it's like, it's gonna have to get way wider. And so,
It looks like the bottom one is a lot weaker.
yeah, notice they all foot the bill, but
I mean, it just seems strange that I guess we can talk through it, but the biggest one, potentially most expensive, it's not gonna do the job that
yeah, that 3.5 by 16 does, and it doesn't even weigh as much. And that I value that I was just talking about, moment of inertia, that we'll be looking at again a little bit more next week. I've told you about it. BD cubed over 12 is how you calculate it. Notice those numbers here. This one has a 1200 number. This one drops to 1190, and this one drops to 732. Tall, thin beams are better, and they do more work for less wood. Now, in my case, when I'm designing a house, a lot of times the floor joists between two floors are 11 7/8. And so if I choose a big tall beam and it's a 2-story house, then either part of that beam sticks down in the ceiling or part of it's on the floor upstairs. Unless there's a wall there, I can't have like a beam in the middle of the floor. So if it's a tall ceiling and it hangs down, maybe I don't care. Maybe I do care because it's in the middle of the living room. It's like, what's that beam doing there? It's kind of okay if it's between the kitchen and the living room because it creates a separation. But a lot of times I might have to spec that bottom one, even though it's going to weigh a lot more and ostensibly cost a lot more. I mean, it's more wood. It seems like it would cost more.
that's kind of cool. And take aesthetics into consideration.
Yeah, that can be the deciding factor. And by the way, notice this is kind of interesting too. What do you notice about the pattern of the shears of those beams? It got worse and worse as far as eye, but it got better and better as far as shear. That's because it's more wood. The only thing that matters for shear doesn't care what direction, like who's tall, who's wide. It's just more wood on the bottom one. Well, it's stronger then. Interesting, huh?
Yeah, I was thinking about not the aesthetic portion of it, but how that guy was talking about how the plumbers took a piece out of their ivy. He's like, that's not the plumber's fault, that's our fault. Like, we should have, toilets can't move. We should have known to move that over and like taken that into account.
Yeah. When I draw plans, I go to the floor plan and I copy all the toilets in the house and I grab the front corner of the house and I paste them onto the floor joist plan. So the toilets are sitting on the floor joists. And I don't go to the trouble to tell them to cut around them, like, move that joist or do something of that nature, but I draw them in there so that they can know ahead of time.
Is that, like plumbing, that's a big potential, well, weakened spot in your plan there, like anything that you're going to drill into the floor?
Well, what you do is if you have, that's not right. If you have joists every 2 feet like this, and then you decide, oh crap, there's a toilet right here, right on that joist. Oh man, it doesn't have to be perfectly centered. There's a pipe for it's 4 inches, so it could be off center and still be in the way. Then what you can do is come in here and take this joist out and then run a joist here and here. And then this part of that joist can stay there. And then you head it off like that, basically. So it takes a little more trouble.
Weaker area?
A little bit, yeah. You can mitigate that by doubling that joist on both sides. Now it's going to be strong enough to carry that. And the other thing is like the toilet itself, the little hole for it is 13 inches away from the wall, and that's all you have to have. So you could actually just put the joists here and here, which actually that'd be better. But you know, does the framer know that that's 13 inches away? Probably not.
The hole, oh, like 13 inches away from the.
Yeah, if you got a wall right here, and this is where your toilet's going to be, it's always against a wall like that. You have 1 inch here because you keep the toilet off the wall, and then it's 12 inches to where to the center of the pipe. That's how toilets are designed. So if you go 13 inches to the center of the pipe, that's 13 inches from the wall. That'll be the center of the pipe.
You're not, yeah, that's such a useless piece of information.
Right? Yeah.
Yeah, exactly.
Let's see. What are we going to do with this? Do the whole thing in 6 minutes? Yeah. I think I might just say part of it. Do you agree it's a combination of the things that we've looked at in the sense that the two sides are cantilevered out? But let's just see if we can calculate that weight there. Because if we can do that, then we can take its integral and so forth. So a lot of this is not complicated, but that part kind of is. And so let's just see if we can quickly play with that, and we'll leave it at that. Let's give myself a little bit more room here. So, see those cat-like reflexes? What's the slope? Because it's a line. Like this is a linear load. Like a second ago, we had 15x minus 10, or actually negative 15x plus 750. It was a line. It was a linear equation, and then it jumped to a parabola in shear land, and then it jumped to a cubic equation in moment land. This is going to be a line. And so what's its slope? Well, notice it runs, slope is rise over run. The rise from one of those to the other is from 40 up to 127. Do you agree with that? Last time it was just 360 was the rise, but this time it goes from 40. And in what distance does that happen? Oh, 12 feet. So when I take 127 divided by 40, I get 87 over 12, which works out to be 7.25 and negative. I should be. So that's my slope. Well, because the weight is down.
Okay.
Yeah. So, you know, you're looking at it as like, isn't that a positive slope?
Yeah.
Yeah, but we're just calling it negative because the arrows are facing down. It's negative because of the arrows. So that means in equation land, I can say y equals mx plus b. It's negative 7.25x plus b. You know, again, I'm not really calling that y. I'm saying that's the. Okay. Except that we said that, well, if we're going to call x, you know, the distance from here to wherever we happen to be landing in that, x is really x minus 28 because I got a 20 and an 8 there. Do you agree with that? So I'll say better w equals negative 7.25 x minus 28 plus b. Now, how am I supposed to figure out the plus b? Well, this is the cool part. Do you agree that when x is 28, aren't I supposed to get 40? I mean, isn't that what it says? It says, hey, that arrow right there is 40. Where is that? It's at x is 28. Or 2, when x is 28 plus 12, which is 40, at 40, I need to get w equals 127, right? And I should be perhaps a little more precise as we were just discussing and say those are negative numbers, right? So plug those in. Let's see if we get the same answer for both. They're both supposed to be true. So let's just take our time with this portion and say, okay, let's see. W is supposed to be negative 40 when x is 28.
So that just makes b
So notice 28 minus 28 is 0, so you end up with B is negative 40. Does that make sense? Like, oh, the top one's the good one to do. That was easier. What's the bottom one say? The bottom one says when W is negative 127, X is 40. What does that give you for B? What'd you get? Yeah, it should be no surprise that you get the same exact answer to this because this is a line and that's how lines work. No matter what point you pick on the line. So therefore, I can say that W equals negative 7.25 times X minus 28 minus 40. Now remember, I got to take the integral of this thing. So wouldn't it be better to say that equals negative 7.25x and actually distribute negative 7.25 in to 28, get a positive answer, and then subtract 40 from it? Does that make sense? Which ends up being 163. So there's my weight equation. And again, if I want to test it, does it make sense? I should be able to go here and like come back from the start and say, oh, okay, I'll plug in 28 and make sure I get 40. And then I'll plug in 40 and make sure I get 127. And that will kind of prove that my weight, my kilonewton per meter function is working to produce the weight no matter where I happen to land. So it's working at the two endpoints, and then it's going to tell me everything else in between. Isn't that cool? Now, armed with that, I don't have to suffer near as hard to get the rest of them. So let's do this and then we'll quit. So basically I have the weight. And so now let's go try to get the shear. And remember, this is kind of only true because we're including that section. Do you agree this is from 28 to 40? In other words, this is where X is between 28 and 40. Everything we did here is kind of under that assumption because we're only looking at that chunk of the load. The rest of it, we said, oh, we're okay at that. We're not great, but we're okay at that rest of that. This is the hard part. Okay, well then let's go get next the integral of that W, which will tell us the shear. Oh, okay, that's not hard. So the shear is equal to negative 7.25 x squared divided by 2, but negative 7.25 divided by 2 is negative 3.625. The integral of 163 is 163x. And then, ooh, I got this unknown. How do I find it? Yeah, back in the original answer we had back here, we need to know what W is. What is that equal to at where this left off or where it started, which is at 28. I got to stick 28 in there to see what that number is. Is this right? And actually, I think this is, yeah, I don't think this is true. Yeah, it's kind of like we might need, I think we might need the shear at that first section, which is going to take more time. We won't do it. So we'll have to find B, and then.
And that's the easy part. So we do the reactions at A and B, and then we do 0 to 28, or I guess we do 0 to 8. So this is a 4-parter, 0 to 8, and then we get our shear for that. But then.
Yeah, that's right. It'd be a 4-parter because you have 4 dimensions there. And so does it make sense? The shear all the way through here is just going to be 540 because of that 540. But then once we know what A is, let's pretend, and I'm going to erase this because it's not going to be, well, actually, I'll tell you the right answer. That ends up being 744. So as soon as you hop past that, now you have 540 going down, you have 744 going up. When I subtract those two, I get 204. Which means, yeah, so like here, the shear is equal to 540. Here, the shear is equal to 204. and then I'll hop into that next section.
And so we plug
Now-
in
Well, notice the shear is 204. In other words, when I'm right here, isn't the shear 204? So that's my starting value here. In other words, if I go back to here, I say, oh yeah, okay, at x equals 28, the shear is 204. So I needed to know that. I didn't have to plug in anything only because it was just a nice straight load. It wasn't some complicated formula. So if you decide to look at this later, I'll just tell you the right answer then. It is minus 1518. So now we have that. Yeah, everything here is based on the 28 to 40. It's kind of the hard part of this.
the hardest part was figuring out that. Because I was like, that's.
I thought last term you were showing us the formula for a trapezoid. Or I would read both like
I
that.
broke it into two pieces
Yeah,
later.
yeah.
I forgot.
See, if we're doing this by hand, we'd have to break this into a 40. We have a 40 load all the way at the bottom there. And then this chunk right here, when we subtracted a second ago, we got 87. So we'd have an 87 blue triangle like the 360 we had a minute ago. And then we'd have a 40 load all the way across this. We'd have to do both of them kind of separately, like two separate parts. So instead of having just one load there, we'd probably just have two. And we did say that we could come up with a way to get it to one, but it's like, it seems like too much trouble. It's only two loads. And if I'm trying to draw a shear for each one of those, that's just two different numbers, a blue number and a red number. So that's why that trapezoid is kind of a step up.
But then we're bypassing all that.
Yeah, that's the calculus of this, where we just say, "Oh, I'm just going to take an integral, then I don't have to draw all that stuff." It's actually a significant shortcut, which again is what chapter 6.2 is about. And so then quickly last, if I said, okay, well then if you take the integral of the shear, then you'll get the moment. Okay, what's the integral of that? Negative. So I take the squared and it turns into a cubed. I divide 3.625 by 3 and I get 1.208 x cubed. I take 163, it becomes x squared. I divide by 2. 163 divided by 2 is 81.5. 1518 grows an x. And then I have this unknown. And so I'm going to have to know the moment of the previous section for this, and I'm not going to take the time to calculate that to let you guys out, because the moment for this section will be 204x, but this b is not going to be 0. In other words, I need to know what that is. I'm not.
So that 540 was
The 540 will be 0. That's exactly right. And so
it'd be 540 times T.
that's exactly right. So this 540 times 8, 40 through 20, thank you, you said that out loud. So that means this one also has to be 4320 at x is 8. And so that'll allow us to figure that one out.
So B will be 58.
What'd you get? No. Wait. I got negative 59.52 for that B value.
And this 4320 equals, and then 204 times B is 1632, right? Plus B.
Yeah, so you'd be taking 4320 minus 204 times 8. 4320 minus 204 times 8. Uh-oh. Yeah, I got a different answer than I got before, so now I'm not so sure.
4320 minus, yeah.
Oh, actually, I know what's wrong. Remember these are negative. This B is negative 540. This B is negative 204. So that's actually a negative number. So you should actually be adding 4320.
Plus 5.
let's see, well, kind of, notice that makes this moment negative 540x, which makes this moment negative 4320, so. So it's actually negative, B is negative 5952. Actually, no, actually, I think I don't have a negative written for 204. I don't think it is. I think mine's wrong because I'm looking at my answer over there and I see my equation doesn't have this negative in front of the 204, which makes me think I probably got it wrong.
So you'll get negative 260. Negative 4320 equals positive 204x.
Yeah, and then we could take that equation and see what we're at 28, and then we'll finally be able to get the equation we're after.
But your almost false equation or your answer for negative 5952 might be wrong.
I think it is because I don't have a negative in front of my 204, so.
Big old question mark.
I'm actually not sure, like I might have just wrote it wrong because I thought I checked this over pretty carefully, but. Because I did work this out already, I think I might take a screen picture of it. Like I'll double check to make sure I didn't screw it up, but I'll take a scan of it and I'll include it in the notes for today, even though we didn't have time to finish it because we just don't have time to do this anymore, but.
That's fine.
The other thing I would say is I'm a little concerned that the 6.2 assignment, because I have 6 questions there, you know, given how long that just took us to do this, I'm feeling like, you know, is that a little bit too, is there more there than we need? I mean, off the top of my head, I would say do 4 of them, like don't even bother to, and on the test, I'm going to make it something a little on the easier side. I mean, it'll be like this in the sense that, you know, but maybe it'll just be a rectangular load. Maybe I'll move the supports around a little bit, something like that. I probably wouldn't put this question on there because that would take your entire time and it doesn't take much to screw this up and we didn't have time to practice it, so. Lastly, I have the review for this last test up now, so you can start playing with it.
2 more classes left, right?
2 more and then you have to